Okay, all right. Well, happy Friday, week 7 Friday. Just a few weeks left now. Week 8, week 9, week 10, and then I guess our finals, graduation, maybe. Um, this Monday, so week 8 Monday, I'm going to cancel our class. I'm doing an exam for a different class, and I'm gonna. Well, anyway, so. So take Monday morning off, okay? And then we'll pick up week 8 Wednesday. All right. So for this class, take Monday off. I'll send out an announcement just so you have it in written form that's what's happening. Okay. But let's go ahead and pick up where we left off. So we introduced support vector machines on Monday, and we said we're looking for this thing with a maximum margin, and then we did some stuff with vectors, and we said, hey, this is, once we get it into this form, which is very easy to read, we can just say, all right, what we're going to try to do is we're going to try to maximize it, and we said we can do it, I guess, with quadratic programming. We can find the vector that will maximize the margin. And in its kind of original form, we said everything, the hard margin says everything has to fall on one side, will be the same class. Everything on the other side of the line has to be another class. And we can kind of relax that with this idea of having a soft margin, okay? And so if we kind of put a cap on how much influence a single point can have, or allow for either values to enter within the margin or even be on the wrong side of the margin, we can have our model can be a little bit more flexible and accommodate situations that are not necessarily linearly separable. Okay. We want to further expand this by using what we'll call a kernel function. Kernel is one of those weird words that show up in these different mathematical contexts, and they mean like totally different things. And so it's like, hey, we have a kernel this and we have a kernel that, and you're like, is this the same kernel? And no, they're just different. I don't know. We just like to use this word kernel all the time. And so here we've got this thing called, I guess, a kernel function. This is also known as the kernel trick. I don't know why we want to call it a trick, but it's just it's a thing where, when we have this idea of drawing a boundary, this maximum margin boundary in this form, and part of it is we take the inner product of our observations, the x values in our observations, and we take the inner product. In part of our calculations, we're going to compare every point with every other point. So we have m1 through n and n1 through n, and we take the inner product between point 1 and point 1, point 1 and point 2, point 1 and point 3, point 1 and point 4, all the way through n. And then we go point 2 to point 1, point 2 to point 2, point 2 to point 3, point 2 to point 4, and all the way through n. And we go all the way up to the last one where we reach n, and we get n through 1, n through n with 2, n to 3, and n to n. And so you have this big n by n kind of matrix of all of these inner products, or x transpose x business. And we can do something with a kernel function that basically takes all of the same kind of combinations, but rather than just doing x transpose x, we do something a little bit different, and we do this kernel function. And what this has the effect of is we still have these inner products, but now we can allow for kind of, I guess, non-linearity. Okay, we can allow for non-linearity, and at a certain level, we can think of this as projecting our two-dimensional, or not our two-dimensional, our x existing in a lower dimensional form, like d dimensions or 2 dimensions, and then when we do this, it's kind of like doing x transpose x, but it's like we've projected it into a higher dimensional space. And so we can say a kernel function can be found directly using xm and xn, but a kernel function will also have an equivalent form, which is the inner product of basically of our x vectors after applying some kind of transformational function phi to the original vector. I feel like I'm just speaking gibberish words. Maybe maybe a little demonstration video I think will be helpful. Let me. Here's my video. Okay, let's watch this video first. Okay. Oh, we have to sit through an ad. Okay.
Watch this. Where it goes. That's hard.
Okay. All right. There we go. Okay. All right. So this is. Oh, this video is 16 years old. My goodness. Okay. It's like as old as some of you. No, not quite. But this will become true in a few years. This video will become older than my students. Hopefully it will still be on YouTube. It's still a great visual. Okay. What we're going to see, okay, is we're going to start off with points that are not linearly separable. Okay. And what we do is, so the points in their original form will exist in 2 dimensions, right? We got an x1 and x2. And what we do is we apply a transformation function, which is going to project the values from 2-dimensional space into 3-dimensional space. So so here is going to be the coordinates. Basically, we have our x1 and our x2 coordinate, and then we have some kind of rule to kind of project it into a third dimension here. So our third dimension will just be x1 squared plus x2 squared. So that's fairly simple, but but this will now project our values into 3-dimensional space. And when we do that, then we can draw a linear boundary. So in 2-dimensional space, a linear boundary is just a line, but in 3-dimensional space, a linear boundary would be a plane. And the original data is not linearly separable. After we project it into a higher dimensional space, it becomes linearly separable with a plane. And this little video is a great animation of this. Okay, so we start off of these kind of blue points and red points. Okay, and so right now the blue points and red points are not linearly separable. We project them into this 3-dimensional space using the kind of x1, x2, and then the third being x1 squared plus x2 squared. And now that we've projected into the higher dimensional space, the values are linearly separable. Okay, and if we project it back down to 2-dimensional space, we have a way to separate the blue from the red. Okay, so we'll just watch this again because it's fun, even though this is back in old school YouTube where the highest quality was 240p 16 years ago. We need an HT version of this. Okay, but again, projected into the higher dimensional space, and in the higher dimensional space, it is linearly separable. Okay. So that's kind of the idea. So, once you can imagine running kind of your maximum margin separator, your the same kind of concept in this higher dimensional space and figuring out your boundary there. And And that's kind of the idea of using a kernel function. So here I've got this transformation function. We take our values x1 and x2, and it projects it to x1, x2, x1 squared plus x2 squared. And we could, if we wanted to, we could go through the steps in the in the first half of the lecture, where we take all of our values, we project it into this three-dimensional space, and then we run kind of the algorithm to get the maximum margin likelihood, maximum margin boundary. Okay, but you don't actually have to transform. You don't actually have to transform it into three-dimensional space, because the values that we ultimately need are just kind of the inner product. Okay, so we just need the inner product between x. We just need x transpose x. Okay, and so we could take our original values, put it into three-dimensional space, and then do x transpose x, and we get just a number. Okay, but we don't actually have to go from x in 2D to x in 3D and then do the inner product. We can just go straight to using this kernel function. And so, for example, let's say I had these two coordinates. Let's say xm and xn were the 0.11 and 0.51. Okay, I could transform them into 3D. Okay, and get 1 1 and then 1 squared plus 1 squared, so 1 1 and 2, and then 5 1 and then 5 squared plus 1 squared, so I get 26. Okay, and so I could do this, and I could say, all right, let's take the inner product. 1 1 2, 5 1 26, and we get 1 times 5, 1 plus 1 times 1, and 2 times 26, and we get the value 58. So I could do this, and I could do this for all of the points, and I can get those values. I could also use the kernel function that is equivalent to using this transformation. Okay, and that would be using this. So if this kernel function k of xm xn is xm transpose xn plus norm xm squared plus norm xn squared. And if you do this, okay, this kernel function is equivalent to doing the 2D to 3D transformation and then taking the inner product. Okay, so here we did the 2D to 3D transformation, took the inner product and got the 58. I don't even have to bother with the transforming from 2D to 3D. I could just leave it in 2D. Okay, so we'll leave it in 2D, and then if we apply this function, we'll get the same number, 58. Okay, so if I leave it in 2D and I have 1 1 5 1, okay, that's going to give me whatever that is, 6. Okay, and then I do xm squared, so that's 1 plus 1 squared, and then xn norm squared, which will be 5 squared plus 1 squared, so I'll get so this is 26 and this is 2, and we can see this will give me 6 and this will give me 52, and when I do that I also get 58. Right? So there's two ways we could arrive at our answer. Okay, I think so. One is kind of using what we saw visually, which is we take our values in 2D, project them into 3D, and then take the inner product, and we get this number 58, and we'll get this for all of, remember, we're doing this for all of the combinations, right? 0.1 to 0.1, 0.1 to 0.2, 0.1 to 0.3, 0.2 to 0.1, 0.2 to 0.2, and we're going to have to figure out this number for all n by n values. Okay, and we can do that. We can also, without having to do the transformation and then the inner product, if we have this function here, okay, we can also get the same values. All right, is that okay? And so that's one way for us to do this. Okay, and so this kernel function, this particular kernel function is equivalent to using this transformation function, and we have other possible kernels. Okay, and so we have these different kernel functions. So if you look at the positive definite kernel, they have all sorts of these things, and I don't know. Okay, so there's a whole bunch of stuff, but we have basically kind of our popular ones I would say, are the linear kernel. All right, so the linear kernel is basically, X transpose X, or here, X transpose Y. So that's nothing, that's kind of like what we had earlier. The polynomial kernel does X transpose Y plus some constant raised to the n power, and there would be an equivalent kind of transformation function. And then we also have the Gaussian kernel, okay, or the radial basis function kernel, all right? And this one says, okay, if you're going to do, 2 points, x and x prime, or, in our case, xm and xn, okay, you're going to take the difference between those things, you'll square it, divide by this, and then you'll do e raised to this thing. So this we can see is kind of, very similar to, there's like if you look at the normal PDF, there's common elements here, right? So this would be the radial basis function kernel, and all of these kernels have some kind of corresponding transformation function. They're equivalent to finding some kind of transformation function and then taking the inner product. But the thing is you don't actually need to know what the actual transformation function is, right? So it's nice to see, like, okay, this function has this transformation function, this kernel function has this equivalent transformation function, and if I transform it into 3D and take the inner product, I get this, and I can get the same value here. With something like the Gaussian kernel, or your radial basis function kernel, the transformation function actually, will take your 2D point, or your point in D dimensions, and when it transforms it, it technically transforms it into a vector of infinite length. Okay, it's based on the Taylor expansion of the exponential function, and so I don't know when did you learn Taylor expansions? 31B, maybe something like that. Okay, and so you have these infinitely long Taylor expansions, and technically each of those elements could correspond to one of the elements in our thing, and so the nice thing is we don't actually have to do this transformation. We're just going to use this kernel function directly. Okay, we use the kernel function directly. Let me give you your view quiz answer. Okay. The first answer today is A. First view quiz answer is A. A as an apple. Okay, so we might get through this quickly. I don't know. This is just a whole bunch of points here, and we can see, all right, there's no way for us to kind of separate this with a linear boundary, right? So this is just an example data set coming from the textbook Elements of Statistical Learning, and we can't separate this with a linear boundary. If we can try, and we'll have to use a soft margin, and we'll try to find the best straight line to kind of separate this. SVM has been implemented using the package E1071. There's probably a few other packages that also implement support vector machines. We're not going to bother trying to do this by hand, okay? And so here you kind of just, what we're going to do is, our Y is the classification, and we're going to say, all right, let's separate our classes here. And so this is kind of the straight line boundary, and it says, all right, this is kind of the best I can do in terms of separating the red from red points and the black points, using the thick line as our boundary, and then I've got kind of these parallel lines, all right? Instead, we can try using a polynomial kernel. All right, and with the polynomial kernel, we have a couple options. One is we can change the degree of the polynomial. So do we project our data into 3D space, 4D space, 5D, kind of this, or actually not even 3D space, 4D. I don't know if there's a direct translation. It's, you know, when we look at this, it's, you know, to what value do we use up here, okay, with a polynomial kernel. And, you know, again, it's all kinds of, the math gets wonky here. And so we have, you know, different values that we can use, and I guess you can just kind of play around with some of these things, okay? So this is one possible thing. And I would say, you know, we're not getting like super great performance. I don't know if this is that much better than the linear boundary. I don't know, maybe. You know, I have all of these points that seem like it's not doing a great job here, okay? If I raise the to a 5-degree polynomial, you know, this seems even worse, right? And then, you know, somehow we have this boundary over here, which, you know, I don't know, okay? But anyway, you can try playing around and just checking different degree polynomials, and I didn't implement like cross-validation, but you could also use cross-validation and say, all right, you know, if this is my subset of data that I want to train the thing on, and then use those boundaries, and we can test its performance on the test set, we could do that and just kind of get a sense. But here we're just going to kind of use visual inspection, okay? You know, one of the most popular kernels is this Gaussian kernel, the RBF, radial basis function kernel, because it is very flexible. Again, one of the things you lose is direct interpretability. Okay, we're just kind of saying, all right, let's draw some kind of boundary, and can we find a good one? And there's two parameters that we can really start changing. Okay, one is gamma, and the other one is cost. And in your homework, there's a few. I think in the homework I have a few plots that use different values of gamma and different values of cost. And even as it is, with those few plots that I've included, it already takes up like, I don't know, 10 pages when you knit it. All right. And thankfully, we're not printing out any of the homeworks. Can you imagine getting like these stacks of homework assignments? No, we're all submitting everything, our PDFs through Gradescope. But even then, I have only a small selection of different gamma values and different cost values. And probably I want to encourage you to actually try out even more different gamma values yourself, and try out even more cost values yourself to really get a sense of like what happens when I turn this knob, and what happens when I turn this knob, and what happens when I turn the knobs together, type of thing, right? So, so anyway, one thing is gamma. You can think of gamma as how flexible is this boundary. All right. Imagine, this is some nasty code here. Okay. Imagine I have to draw like I'm gonna lay like these cables and draw, like I'm gonna try to like trace the shape of this cable here, right? Okay. Which, if I have this, and here I have this really fatty HDMI cable, right? So which one is more flexible? The skinnier one, right? This little thin cord, I can make like tight little corners and whatnot. Okay, so I can get this really kind of flexible boundary here. Whereas this cable, sure, I can bend it, but like now it's really hard to kind of get tight turns here, and that's you can kind of think of this. Like, how tight can we make these turns related to the gamma parameter, okay? So here I've got, this is gamma 0.5, gives me, just look at the overall kind of, I guess, curvature of the boundary here. Here's gamma 0.1, so a lower gamma means like this cable that I'm bending is like really thick and it's hard for me to kind of put tight turns in it. As I increase the gamma, okay, the borders get more and more flexible. So here it is at gamma 10, and I have this very kind of flexible boundary, and I can have these tight little turns and corners. Okay, we also get these, little pockets and enclaves as I increase my gamma to be really high. But what I want you to see is, we get the shape of these boundaries being, allowing for more kind of curvature here, right? So as I reduce the gamma, the boundary becomes less flexible, okay? And so, just kind of eyeballing this, we go, oh, that looks decent. Okay, this, I don't know, you could make a good argument for either of these because, the thing that's being affected is like these points, these areas where there's not really any points. So like, I don't know where you would want to draw your boundaries. Okay, and at a certain point you feel like, okay, maybe we're now like overfitting our data a little bit. Okay, we're drawing this little boundary, this little region out here and something. Maybe we don't need to do that. Okay, so that's kind of the influence of gamma. I'm going to just give you your last two view quiz answers. Letters C and D, cat and dog. C and D for your last two view quiz answers, cat and dog. So that's one thing about gamma. And again, fiddle around with these things. The other parameter is the cost parameter, okay? The cost parameter is kind of like how much influence does one point have, and how badly, like, imagine like trying to minimize our loss function or minimize our cost, and misclassifications will have kind of increase our cost. And so if we have low cost, we're going to say, I don't mind misclassified points very much. And if I have a very high cost, we're going to say we really want to avoid any kind of misclassification. Okay, and it's changing gamma, changing cost. As you increase gamma, as you increase cost, they're both going to have the effect of changing, too high of a gamma, you're going to have overfit your data. Too high of a cost, you'll also overfit your data. But the effects of each one are different, a little bit more nuanced. So again, gamma, I would say, is related to how flexible the boundaries are, and cost is kind of like how much influence does one point have. So imagine having this inflexible boundary, right? This boundary that it's hard to kind of bend this, but you can say, all right, this one point can really apply a lot of kind of force onto the thing. Okay, so here I think I'm going to keep gamma at 0.5. We'll start off with low cost, and I'm going to try bumping up the cost from 0.1 to 0.5 to 1 to 2 to 5 to 10. Okay, so here's gamma 0.5 cost 10. Okay, and we're saying, okay, I really want to try to avoid misclassifications, but I'm also stuck with having kind of this, cable or this boundary that's fairly inflexible. Okay, so here I'm kind of allowing the cost to climb up here. Okay, let's look at. I'm going to now change gamma to say 2. Okay, so gamma 2 is more of a flexible boundary, and here I've got low cost, so we don't mind misclassifications, and this kind of just reflects what we have. As I increase the cost. Okay, so here it is, with gamma equal to 2. As I increase the cost to 10, we can see, okay, some of these individual points are now, influencing the boundary, right? So we do get a little bit more. I don't know what the right word is. I guess we are able to accommodate some of these finer boundaries and points here. But the overall kind of, I guess, flexibility and curvature remains similar with gamma equal to 2, okay? Here it is gamma 0.5, right? And then let's try gamma equal to 5. So gamma equal to 5 allows for like very flexible boundaries, okay? Low cost, as I increase the cost, we get these these pockets, these enclaves, these exclaves, and we can really have these very tight, sharp turns and corners in our boundary. Okay, we get kind of these little pockets. Perhaps this overfits the data, or I don't know. Perhaps we're happy with what we're drawing here. Okay, and so there is a lot of kind of questions in terms of like, okay, do we want to make like a special case and say, all right, this little boundary here in our data gets gets its own kind of little pocket here, or do we just say, nah, you know what, like everybody's got to and once you're out over in this territory, you're in kind of like the red zone or whatever, right? I don't know. We can use cross-validation to try to figure this out. This is, my hope here is this gives you a little bit of a sense of like how changing gamma affects how our boundaries are drawn. So here I'm keeping cost equal to 1, and we're changing the effect of gamma. Here we're going to keep gamma at a certain level, and we'll change the cost. And again, gamma at a certain level, changing the cost, gamma at another level, and changing the cost. And we get these different boundaries and different shapes. This is all for the Gaussian kernel. You can also try it out for the polynomial kernels. Try changing and altering there. But yeah, support vector machines. It allows us to draw these interesting boundaries. All of these things have been drawn in 2-dimensional space. You can apply it in higher dimensional space as well, and they're useful in these kind of contexts of classification. Well, if you have 2 classes, okay. Today I would say neural networks are just more popular, which is fine. But I think there is some interesting stuff going on still with support vector machines, and you do encounter them in classification settings. When you have 2 classes, and then probably the most popular one is this Gaussian or radial basis kernel. But it's useful to know the effects of these kind of parameters that you can kind of tweak and alter there. Okay. We'll go ahead and end a little bit early today. And again, Monday we'll take off. We'll pick up on Wednesday, and we'll look at some clustering ideas there. Okay. All right. So have a great weekend, and we'll see you Wednesday. Oh, did you get the announcement about the homework deadline? Okay. So that will be homework's due Monday now. So okay. All right. Okay. Have a good weekend. We'll see you next week.